But my name is Vijay. I'm working under Dr. Vijay Muralidharan. So today we'll be discussing about inertial measurement unit based orientation estimation. Okay. Just a minute. So these are the contents. We'll start with some introduction of IMU. What is IMU? What are the sensors that involved in IMU? And what the data it will give? And what is the attitude called orientation? And we'll go with the rigid body orientation. Then we'll come to the mathematical equations which involve in the estimation of attitude or orientation. Then we'll finally see some demo or some experiment in the using Raspberry Pi, how we estimate the attitude using roll, pitch, and yeah. So coming to the introduction part, let's say, so why we need a IMU? Like IMU is the inertial measurement unit, and IMU is in everywhere nowadays. Like let's say, for example, drones, if you take, so drone movement depends upon what are the sensors it has. Let's say, for example, IMU, LiDAR, or camera. So mainly for drones, we use the IMU to estimate the orientation, like a roll, pitch, and yeah. That means the orientation of the drone in some sense, like around its own center of mass, the orientation of the drone. And in robotic manipulators, we use IMUs where the people are not using the feedback sensor based servo motors or feedback sensor based motors for the actuation of robotic manipulators. And recent days, you might be seeing this virtual gaming technology and all. Like movement of the head belongs to the movement of something in the gaming and all. And especially you might be seeing this mobile phone case, where you can convert the portrait mode to landscape mode. Let's say, for example, if you are using mobile phone for the gaming and all, just without touching anything in the screen, just by tilting the mobile itself, you can able to observe the movement of any car in the game or something, right? So, and there is something like wheeled world robots to estimate the orientation, like how it is moving left and right. We can use this inertial measurement unit. So all these applications will be mostly depends on the inertial measurement unit is the main sensor. So what are the type of sensor that having inertial measurement unit? Let's say, for example, accelerometer, gyroscope, and magnetometer. Accelerometer will give a linear acceleration of a body. Like if you connect this inertial measurement to any body, let's say, for example, rigid body or any drone or any mobile robot or even your mobile. So it will have accelerometer. It will give linear acceleration in terms of meter per second square and also it will have gyroscope. It will give angular velocity of the body. And sometimes the inertial measurement unit is also having magnetometer. Mostly it will have magnetometer, but some sensor doesn't have magnetometer. And the magnetometer will give magnetic field or its magnetic field in terms of new micro Tesla or Gauss, right? Let's say one example of IMU is YZY80. It has a separate sensors kind of thing, magnetometer and gyroscope, accelerometer and barometer, something. It has separate sensors. All some sensors are embedded separately. And there are some other boards where all the sensors are combined together and embedded. Right. Let's say, for example, LSM90S1. And this is MPU, a very famous microcontroller, very famous IMU, inertial measurement unit. And if you want to have more accurate sensors, we can go for XSense sensors.
That itself will contain all the other three.
Yes. The small chip itself having all the three sensors like accelerometer, gyroscope, and magnetometer. So when coming to the working principle of each and every sensor having inertial measurement unit, let's say, for example, you take accelerometer working principle. So it has a mass, which is a moving mass, movable mass. It will move like some acceleration, it will create some acceleration movement based upon acceleration. And it has also some capacity, some plates, which is fixed to the body. Like, and there is a capacitance in between movable mass and fixed plate. So where depend upon the acceleration, the mass will be moved, and depends upon the movement of the mass, the capacitance of the capacitor will be changing. And this capacitance will be converted into the some by using some converters and all. They will convert to the amount of acceleration. It depends upon the acceleration, how much it will convert. Now, when coming to the gyroscope, will work mainly on based upon the Coriolis force. That means, let's say we have a rigid body, any body, and the body is moving with some linear velocity. Okay, and if the body also experience some angular velocity, and it will create some Coriolis force. This Coriolis force will also exert some displacement. That displacement will cause again some capacitors change in capacitance, that will convert into again the amount of gyroscope value, how much it is giving angular velocity. So you can see in this animation, it's moving in a linearly first. Whenever there is an angular rotation is happening in this, and it will create some displacement in Coriolis force and around this. That's the principle of gyroscope. Now, when coming to the magnetometer will measure the Earth's magnetic field that we know, and it will mainly works on Hall effect sensor. Let's say, what is Hall effect? So let's say we have the conducting plate, and the electrons are moving from negative side to positive plate in the conducting plate. Whenever the magnetic field is experienced in that plate, and electrons will come to the one side, all the electrons will come and sit in the one side, and the other side will form the poles. Okay, so that there will be a voltage difference will happen in between them. So based upon the how much magnetic field is experiencing the plate, the voltage will be proportional to that value, and it will be measured, and it will give the value as a magnetic field effect. And all three sensors will be kept in a chip, embedded in a chip, and that will be kept in all three directions, X, Y, and Z directions. Okay, and that will call it as a IMU, Inertial Measurement Unit, which will give the orientation or linear accelerations, angular velocity, magnetic field in all three directions, X-axis, Y-axis, and Z-axis. Okay, and we call it as this. All these sensors, we call it as, sometimes we use attitude and heading reference system. Mostly this magnetometer will use for term heading reference system. So now we'll move to the main content, like how we'll develop the attitude of any robot or any drone or any rigid body, and what is attitude first, and how will you formulate that attitude. Let's say, for example, to formulate the attitude of a rigid body, we need at least two frames. One is the inertial coordinate frame, and one more is body coordinate frame. Inertial coordinate frame will be fixed to some point somewhere, but the body coordinate frame will be fixed to the body center of mass. Let's say, for example, this I'm assuming is a rigid body, unless until we are going for the multiple mass body or distributed mass body. So we are assuming this a rigid body. Okay, so it is attached to some center of mass to the body, and this body coordinate frame will be rotated with respect to the body or drone, any drone. Okay, and what is attitude means? Attitude is the orientation of the rigid body with respect to inertial frame, or the orientation of rigid body with respect to its own previous frame. Let's say, for example, initially my body frame can be inertial frame. Like, let's say, for example, see here XB direction, YB direction is in YI direction, but later after some time my body will be moved. So I want to compare my body current body direction with respect to the previously inertial frame. Okay, that is called attitude. That will be given by roll, pitch, some Euler angle based techniques, like some formulation as a parameterization that we will talk. There is something other thing like position. Position means it's not a attitude. Few students will think it as a position, attitude, like same, but it's not. Position is not attitude, because position is like, it's a, let's say, for example, drone is moving somewhere else. So from with respect to inertial frame to body frame, how much it is movement. It has movement, some linear motion happened. That is called position, finding a position. For finding position, we have some other sensors like camera we can use, GPS we can use. If you are staying outside, GPS you can use. So these are the sensors for position measurement of a body or drone. But the attitude measurement will use mostly IMU, and sometimes we'll use camera also for attitude measurement. Okay, now
XYZ will be initially set to some normal sort of thing.
yes, it's a general kind of thing, formulating how rigid body. So let's say now, for example, I'm rotating a rigid body, like the drone has rotated with some angle pi in counterclockwise direction. Here you can see. Okay, sorry. So here you can see it's rotating with respect to XB axis. I'm rotating, the drone is with some pi angle in counterclockwise direction. So we'll get in this form, right? So in this form, if you'll get, but my XB axis is in the same direction because I'm rotating with SB only. Remaining two axis will be changed, right? ZB will come to this and Y. So let's say now we remove this drone. This is the, we'll focus on only vectors now. Okay. So this is the previous frame, this frame, and it becomes as a previous frame. And now this is a current frame of the drone, right?
Yeah.
So now let's say project this current frames back to the previous frames. Okay, if you project the current frame back to the previous frame, we'll get some projection, sub projection quantities. So now we need to formulate this. Okay, let's say for example, xi initial frame x-axis will be xb only because I'm not changing anything in the x direction, just rotating with respect to x. Okay, now yi becomes these two vectors. Yi, this is yi, becomes these two yi vectors along the yi, this one and this one, right? Now zi become these two vectors. Okay, so now we can write these equations in the form of a matrix. So we'll get this form xi y zi equal to some matrix into this body coordinate frame. This matrix we call it as a rotation matrix or orientation matrix or something we can call it as. And that means here takeaway is, let's say for example, I have a vector in body frame. And if I want to represent the vector with respect to inertial frame, if I multiply with this equation, this matrix, I will get another vector in this inertial frame. That is the takeaway from here. So this matrix I'm just representing with the rx into pi because I'm rotating with the x in the direction of xb and with the angle pi. I'm going to just notation. Now that is only one axis representation, one axis rotation will happen, but our drones or physical systems are not only one axis rotation. It has multiple axis rotations. I mean, 3-dimensional rotations will happen, and it has composite rotations also. At the same time, some roll can happen, pitch can happen. Okay, so now how we can formulate that rotation matrix? We can see, because rotation matrix will help us later to form the roll, pitch, and to derive the roll, pitch, and So there is something called Euler parameterization. That means we'll use the sequence z, y, x. That means first we'll rotate with respect to z, then we'll rotate with respect to y, then finally we'll rotate with respect to x axis. Now same thing, inertial frame is there, body coordinate frame is there. So first initially I'm rotating my body frame with respect to z axis, so that zb will be z1, and the rotated frame I'm assuming as z1, y1, and x1, some notation. So new frame, this is new frame, x1, y1, and z1. And this old frame, xb, yb, and zb. So I'm rotating. Then similar to the previous way, we can just project and make it a rotation matrix. We'll get in this form. Rotation matrix will be in this form. Okay. Now we'll take currently rotated frame. We'll forget about this zb, yb, and d. This is previous frame. Now we'll take as it is this current xy, x1, y1, and z1. Now let's rotate this frame with respect to y. That means with respect to y, rotate this, y will be same, but z and x will be changed. This new notation I'm taking as a z2, y2, and x2. Okay, and again project back, and we'll get this equation, rotation matrix equation. Now finally, I'm taking again my current frame, z2, y2, x2. Now I'm rotating with respect to x. So x means it will go like this. Same thing, project back and we'll get this rotation matrix. Okay, where this psi, pi, theta are yaw, pitch and roll. This psi is yaw, pitch and roll, which are colored as Euler angles. Okay, this will represent the drone attitude. Okay, so to get the combined composite rotation matrix, we need just after each and every rotation happen, we just post multiply all the rotation matrices, so that we will get this composite rotation matrix, where C is the cos theta and S is the sin theta, sin pi. You can assume S is sin and C is the cos. Okay, so now I have my body orientations and I have some sensors like IMU, gyroscope I have, accelerometer, magnetometer I have. So these sensors I have, and I want a rotation matrix or any Euler angles, roll, pitch. Yeah. Okay. Now how you can formulate from the sensors data, how you can able to get the rotation matrix or roll, pitch. Yeah. Okay. Body attitude. Okay. So for example, we'll take gyroscope. Gyroscope will give angular velocities omega x, omega y, omega z with respect to body frame. That means, let's say, for example, vehicle frame, PCB frame, or body frame, sensor frame, all are should be same. Even if it is not same, we have to ensure that these all frames should be same by having some rotations and reflections. Okay, so gyroscope will give measurements with respect to body frame. So there is a well-known equation, kinematic equation of rigid bodies. This is R dot equal to R omega hat. Okay, where this is a matrix, right? This is R matrix. So just to differentiate with respect to time and just multiplying with the rotation matrix with the R with some omega hat, where omega hat is there. Let's say, for example, omega is omega x, omega y, omega z. This is a vector, and this vector will be converted into skew symmetric matrix. Okay, and this formation will be done with the omega hat. So by doing this and formulating this and by solving, we'll get omega x, omega y, omega z as a this form. These are pi dot, theta dot, and psi dot. Okay, and like to get the Euler angle rates, that means we want Euler angles, right? First we'll form Euler angle rates. So to get the Euler angle rates, we need to do inverse of this rotation matrix. We'll call it as a transformation matrix usually. So we need to do inverse of this. But the drawback here is with the Euler angle parameterization, this let's say, for example, if I do the determinant of this is a T, I'm assuming transformation matrix. If I do the determinant of this, we'll get the cos theta, and which is has a singularity here to theta equal to plus or minus 90 degrees. So this we call it as a singularity issue, and it's not a much difficult thing. Like we can see in the while explaining this using the Raspberry Pi, some demo. So now we have this Euler angle rates. Now just by doing integration, we can able to get the Euler angles. That means pi, pitch, roll, and yaw attitude of the rigid body. That will get. I mean, this is the current value. This T means I'm assuming the previous value plus this delta T into delta T will get the current attitude. Okay, roll, pitch, yaw. But the gyro readings are not the true readings. That means it has some bias, omega B, and also some noise. Like let's say omega B is some bias and a noise. That means every sensor has some noise and every sensor has some bias. Usually bias will reduce by doing some calibration. Let's say, for example, what is the bias? How this bias will be affecting our data. Okay, so let's say gyro is giving some values. Let's say we are keeping our sensor at the ground. We are not touching the sensor. We are just keeping at the ground. That means it should give literally it should give 0, 0, 0. Say x, y, z. There is no movement, so it should give x, y, z equals 0, 0, 0. But if the sensor has some bias, that means some constant value, some fixed constant value, so it is always present there, right? So if you're integrating, to get the attitude, that means to get the roll pitch, yeah, we said we are integrating, right? If you integrate this, integration of a constant becomes a drift. it will be depending on the time, like over a period of time, it will drift over a period of time like this, right? That means if even though you are keeping your sensor at the ground without touching, it is showing some position variation, right? Some orientation showing, right? Some orientation in roll or pitch, yeah, it depends upon the data. It is showing some non-zero value. That means it is a drawback, right? So this bias can be reduced by doing somehow calibration, but complete removing is not possible because this bias also sometimes slow varying time dependent variable. Okay. So this is the drawback in only using gyroscopes. So that's why people usually use multiple sensors along with the gyro. Some other sensors are accelerometer, magnetometer, they will combine and they will use. And this sensor can be used only for shorter periods because it has a drift. So we can't trust it, the sensor for longer periods. Okay, for shorter periods, it will be good. The sensor will be good, gyroscope. So this is how we are finding the roll, pitch, and yeah, by using only gyroscope. Next, by using accelerometer and magnetometer, how will you find the roll, pitch, yeah? Okay. Usually, the accelerometer will give linear acceleration, AX, AY, AZ. So people can say that by simply double integrating, we'll get the positions of the drone, but it's not possible because here we seen just with one integration, we have a lot of drift. If it is double integration, it will be like a exponential or some kind of drift will be there. So people won't use this accelerometer for linear position estimation, and the accelerometer will be used mostly for angular position, angular orientation estimation of the drones, right? So this linear accelerometer will give linear accelerations with respect to the inertial frame. So let's say, for example, I'm assuming this is my measurements of the accelerometer, AL, that means linear acceleration, along with the acceleration due to gravity, right? So the accelerometer will measure the acceleration due to gravity also. So I'm just separating these terms, and I'm assuming this linear acceleration AL is very small because the acceleration for an orientation body is very small.
AL is the acceleration you are receiving from the accelerometer, right?
Yes, this both are from accelerometer only. I'm just dividing this normal accelerometer acceleration values along with the acceleration due to gravity. It will also pick up the acceleration due to gravity. Okay. And I just want to represent this accelerometer values with respect to body frame. That means I'm just pre-multiplying with the rotation matrix transpose. Pre-multiplying with the rotation matrix transpose will give the values with respect to body frame. Okay. So this vector form I just shown here, where G is 9.8 meter per second square, that we will call it as 1 unit. 1 G equal to 1 unit we call it as, because we are not much bother about magnitudes. We are just bothering about vectors only, right? Even later magnetic field also, we are not going to bother about magnitude of the magnetic field. We are just thinking about the vector of the magnetic field, how it is, in which direction the vector is. So here R is R transpose, we can form like we know R, and just by transposing this, we'll get R transform. So this assumption I already said, AL equal to, we are assuming this some theta because it's very small. Practically, it is not possible. That also a drawback of this, but we are assuming this is AL equal to small. So by substituting this, we'll get on this form, like by substituting this R transpose also here, and we'll just in this form. Right, we have only minus sine theta. This vector will get right here. Okay, by solving these vectors, we'll get pi as a roll, theta as a pitch. Right, simply tan inverse. That means by just doing this, these two divided by, we'll get this. Right, so something like that. We'll get pi and theta, roll and pitch. But with just accelerometer, we can't able to find ya. Ya means it is a rotation around Z axis. Pi means rotation around X axis. Theta means rotation around Y axis. So, but the rotation around Z axis, we can't able to measure because let's say, for example, if you're rotating in X axis, the gravity vector also will change, right? So it will give values, accelerometer will give so different values in some all other, right? But if you are rotating in Y axis also, gravity vector will change. Let's say if you rotate in, gravity vector will change. But if you're rotating around Z axis, gravity vector won't change. It will be always down only, right? So that's why the accelerometer can't pick up this rotations around Z axis. So for this, we need again magnetometer. Magnetometer is needed for this. So now we'll come to the magnetometer. Magnetometer will measure the Earth's magnetic field in terms of micro Tesla. Okay, some sensors will give in terms of micro Tesla. Some sensor will give in terms of Gauss. Okay, you might be seeing this 2D magnetic compass in somewhere whenever we are in childhood. But this 2D magnetic compass will give only magnetic field in the north direction. But this is not actual true measurements because it is 2D only, right? It can't able to move in other direction. It is 2D only, right? But actual real magnetic field will be little somewhat down. This needle should go to somewhat little down, but it's not possible for this 2D constraint, right? So real magnetic field will be little down. So the horizontal component of magnetic field will be in north direction, and the vertical component of magnetic field will be in the downwards, right? Even we are not bothering about this magnetic field magnitude B, that we will see later, that we will see in the next subsequent slides. So this is the observations or measurements from the magnetometer. And if you want to measure how much inclination is happening, that there are some famous websites, maybe these links are there. There are some famous websites so that you can use the measure. Let's say, for example, in India, we have around 20 degrees inclination. And whether it is positive or negative, up, down, that depends upon how we are taking the Z axis, whether vertically upwards we are taking Z axis or vertically downwards we are taking Z axis. Okay. So now let's say these are the measurements. Let's say, for example, my beam measurements with respect to body frame, because my magnetometer will give measurements with respect to inertial frame only. So I want with respect to body frame measure value, and this is B true. And magnetometer is also not a true measurement sensor. It also has some soft iron effects and hard iron effects. Let's say, for example, if you are keeping this sensor in the drone have this BLDC motors, right? So BLDC motors are having some coils. So if you current is flowing in that, it will excite and it will create a magnetic field. That magnetic field will be somehow disturbing the magnetic measurements of the magnetometer. So that is called as some soft iron magnetic field, something. And let's say you have some screws, iron screws in the drone or some any screw kind of thing. That will also affect this magnetometer measurements. So that we call it as a hard iron effects. Right. Those all things will be represented with some W and V. V is some kind of hard iron effects, and W is kind of some soft iron effects. So how we are forming this model means that we have to check in some other papers or something, because sometimes usually we add this noise or something, but why we are multiplying this, that depends upon the model of this. Okay, how we are formulating this, and by pre-multiplying with rotation matrix, we'll get in this in the body frame. So similar to accelerometer what we done, just I'm just taking this R transpose rotation matrix in this form, Rx transpose, Ry transpose, Rz transpose. Okay, and just showing this B true values in vector form. And these are the hard iron effects, and these are the my actual values in terms of body frame, right? And I'm just keeping this RZ in same in this frame, and remaining everything I'm just sending to the LHS side. And by just formulating this, I will get these equations. Okay. And from this, if you solve this, we'll get psi. This is the psi means heading, or we can call it as heading something. Just by doing divided by these two equations, we'll get this psi. Right? This psi. So now how many we have? So we got all three: psi, heading, or and roll, pi, and theta. Okay. So these are the values from accelerometer and magnetometer. So accelerometer and magnetometer also have some drawbacks, which are already discussed. Accelerometer has sensitive, like we assume that linear accelerations are not there, but in practical it is not possible. right? It has some moments, it will pick up that moments also, linear acceleration. And it is very sensitive to vibrations also. Even if it has very small vibrations, it will pick up. That small vibrations are high frequency vibrations, high frequency noise will be there, right? And magnetometer also affected by some hardware and software and effects. So it also has some high frequency noise. So even though the magnetometer and accelerometer can be trusted for longer periods, but it has high frequency noise, right? It will, so only if you use the accelerometer and magnetometer, it will have a lot of vibration. Drone will vibrate like anything. So that's why usually people will suggest to go for the combined both the accelerometer, gyroscope and magnetometer. That means that is, we call it as a sensor fusion. There is a concept called sensor fusion, where we take all the sensors, we'll fuse the sensors, different sensors, then we'll get the better estimate from output of the fusion, right? That we call it as sensor fusion. We have several techniques for sensor fusing. Some of them are like a complementary filter, Karman filter, and particle filter, right? Among them, complementary filter is a simple one that we can explain today. A Kalman filter, I'm not going to explain that. People can go through that, some papers or something. It has something like complementary filter only. It will be easy. It's not a difficult task. Okay. So the typical arrangement of a complementary filter will be something like this. Let's say, for example, I'm taking one measurement, either pitch or roll or any, yeah. Let's say I have some measurements. So this measurement has true value and along with some noise. Let's say I'm taking this from accelerometer, true value plus noise, and some other measurements from gyroscope. So true value plus noise plus bias. Gyroscope, we don't bother about noise because gyroscope has much robust with the noise. It won't pick up much noise, high noise. So we'll neglect this value. So this noise measurements will send to the low pass filter. That means accelerometer values will be sent to the low pass filter, so that high frequency noise will be rolled out. And also this gyroscope measurements will be integrated because we want to get the roll pitch, and then given to the high pass filter to remove the bias or to remove the drift, right? And then will be combined together to form a better estimate of the actual measurement, right? So that it has both the benefits of high frequency reduction, high frequency noise reduction, as well as drift reduction, right? So just there is something like we can discuss this low pass and high pass filter. RC, you might be seeing this RC low pass and RC high pass filters. It doesn't mean that we are connecting a resistor and a capacitor with the data lines of the IMU sensors. It's just an interpretation how we can formulate the low pass filter and high pass filter, just an interpretation. So let's say, for example, RC low pass filter. You might be know this, how to formulate this transfer function of the low pass filter, omega 1 by s plus omega 1, where the omega 1 is the bandwidth or something, or cutoff frequency, omega 1. For this is the Bode plot or characteristics of the low pass filter. Okay. And if you take high pass filter, this is the transfer function of the high pass filter, and the characteristic will be in this form. So since we are in the complementary filter, we are adding both. So it will fuse some kind of all pass filtering properties, right? But the cutoff frequency of the two filters should be same. Then only we'll get some all pass filtering. Otherwise, we'll miss some data. We'll miss some frequency ranges of data, right? So the how we can find out this cutoff frequency exactly what we need, what required means there is like we can do some DFT, discrete Fourier transform or FFT. By doing FFT, just take some data we can store from the accelerometer or magnetometer or any sensor, and you can find the FFT of the data so that you can able to find what are the frequency components present in the data. Then we can reduce we have to decide how much content we can reduce from the data. Okay, that will be decided by this omega 1, omega 2 cutoff frequency, right? So theta hat is estimated like combined both estimated value will be something like this. So by adding, I'm just adding it. I'm adding two transfer functions with this value. we'll get in this form. So by just doing this time domain, we can get in this form, just converting into Laplace domain into time domain. This is the dynamics of the filter. Okay. And there is something called, we can able to estimate the gyroscope bias also in this form. There is some papers, famous papers you can see. We can also estimate some bias by just adding some forward path for this. So we can able to estimate the bias of gyro also. Now, I think we can discuss remaining things later. We'll go to the Raspberry Pi part. Just a minute. So I'm assuming people know at least some extent about Raspberry Pi, how you can connect Raspberry Pi, how we can install the recipient software in Raspberry Pi. Even if don't know, it's fine, no problem. It's not a complicated task. I have formulated some document. I will share this document to you. It's not possible to discuss everything at one shot, like within 1.5 hour. So I just formulated how to download the recipient software, how to set up the Raspberry Pi, and how to do SSH. Okay, just go through this. It's just a simple task only. It's not a difficult task. Visible, right? I hope you can see the two screens, right? Can anyone unmute and say, can you able to see this Raspberry Pi?
Yes, yes.
Okay, fine. So this is Raspberry Pi. You can see this. And this is IMU, Inertial Measurement Unit. This is the LSM90S1 that will see now this data sheet of this LSM90S1. So this is the IMU. It has the all three sensors, accelerometer, magnetometer, gyroscope, that you can see from this. This is IMU. Okay, it has two types of interfacing. One is I2C interfacing and SPA interfacing. This is also something you need to go back and check what are the interfacing techniques available, like serial peripheral interfacing techniques. Let's say, for example, I2C, UART. If you are working in drones area, or if you are working in especially estimation kind of thing, robotics, definitely you need this interfacing techniques like UART, SPI, I2C interfacing techniques. So we'll check the data sheet of this. So you can able to see, right? This is the data sheet of LSM90S1, the IMU what we are using. So first thing, if you want to implement anything, let's say, for example, any motors, any IMU sensors and all, first you have to check the data sheet, right? So this IMU will work for 3.6 amp voltage, right? Some IMUs will work for 5 volt also, but this will work for 3.6 volt only. And let's say so this is a block diagram of all the sensors, 3 sensors, like accelerometer, and this is the gyroscope and magnetometer. if you observe this X, the coordinate frame of each sensor is different, right? It is a, let's say for example, left-handed coordinate frame. It has left-handed coordinate frame. And this is also left-handed coordinate frame, but the magnetometer is not, right? Magnetometer has some right-handed coordinate frame. And the axes are different from this. That's also something you have to take care. You have to convert this axis into all universal axis coordinate frame. Let's say you can just convert this x to minus x so that it will give you in some accelerometer coordinate frame, right? Something like that. I will show you the code also, how we can convert and all. So now we'll go to the, I'm using this VNC Connect server to enable to access share screen of my Raspberry Pi. You might be seeing like Autodesk or some default Windows screen sharing applications are there. Something like that. VNC also one of the screen sharing application which use mostly Raspberry Pi. So I'm opening this Raspberry Pi. So this is the screen for Raspberry Pi. This code will use mainly. I already formulated the code. I already prepared the code because it's very difficult to write the code and all within just a short period. So I just given everything. I'll just explain every step of the code. I will just explain. Okay. So I hope at least some extent of basics of Python is everyone having, right? Or even if you don't know, it's fine. No problem. We can just go through this once. Okay. There is something called SM bus. That means SM bus is a, let's say for example, this we are using I2C. I'm using I2C communication for this Raspberry Pi, my Raspberry Pi 2. This is my Raspberry Pi 2 is my sensor, LSM90S1 sensor. So I'm using this communication through I2C communication, right? To enable I2C communication, I need to use some package called SM bus package, right? So SM bus package, I'm just initializing this SM bus package. Okay. Then I'm just importing some tools, count and all. This is not needed actually. So we'll see later. And then I'm importing math tool, and I'm importing NumPy, numerical pi, and scientific pi. I want to use some linear algebra equations. These are just packages where some functions are available, like ready-made functions without typing under. We can use directly these functions, right? Now, let's say, for example, you might be studied about microprocessor. So microprocessor is called something like, let's say, for example, it has some registers. Let's say, for example, I'm in the Palakkad town. Let's say Palakkad town is assuming it as a entire IMU. Yes, entire IMU, Inertial Measurement Unit. And it has some streets, different streets. I'm assuming as some magnetometer, accelerometer, different streets. So each street has some representation of number, something like street 1, something street 2, something like that. Similarly, for each sensor also, it has some address, right? Some address. Let's say how we have our home, we have address. Same way, each sensor has some address. Okay. If you want to write something to the sensors, or if you want to take something from the sensors, it has some address. We have to represent that address, right? And again, each sensor has their own registers. The registers are something called like some input registers, output registers. Let's say, for example, this CTRL register 1G, these registers are belongs to the gyroscope. And these registers belongs to the accelerometer. Right? These are some combined registers. Okay. And these are out register. That means it will give data. So if you want to write something to the sensor, we have to write in this registers data. These are the address of the register, right? Each register also having some address. Okay. If you want to point out these registers, we have to use this address. If you keep this address only, it will go to this register. The data will go to this register. Okay. These are the out registers where we will take the data. That means the sensor will give the data, some values like accelerometer values and all. Similarly, these out registers are for accelerometer. Okay. Now, similarly, this magnetometer has this control registers, some control registers, and also some out registers. Okay, these registers and all given already in the data sheet. Let's say we go to the data sheet. So each and every application of this register, it's given here. What are the registers and what type of data we can give? Okay, and what type of data we can able to get from the out registers, right? It's given in the data sheet. So now I2C communication has, first we need to, like, let's say for example, first we need to give some data, then only it will give back to the data, right? So we have to write some data to the registers. Let's say for example, so I'm writing some data to this address, accelerometer, with this register. Okay, this data I'm writing with this register. Okay, so each and every bit has some meaning. It has OB, 0B means it is a bit. Here OX means it is a hexadecimal number, right? Each bit has some meaning. Let's say for example, here I'm using 111 means it is enabling all three axes, X, Y, Z. I'm just telling to the sensor that enable all three axes, X, Y, Z. Okay, that means what we are writing here, right? I'm just telling to the sensor, just enable all XYZ axis. I want to access all XYZ axis data, something like that. And let's say for example, some other register I'm writing, it'll take full scale value 11, or you can, I want data with 467 hertz. That means I want data rate that much fast, like how much frequency, how much fast we need, how much data. That will be decided by data rate, right? I want data from 476 hertz, right? That I will write here. This is called how we are writing the data to the sensor. I'll write data in the accelerometer sensor. I'll write data to the gyro also. We'll also write data to the magnetometer, right? Now it's time to take data from all the three sensors. For that also we use this read by data application, the read by data function. So these functions all will come with the SMS package only, right? So now if I use this read by data and I'm just telling I want data from accelerometer, and it will give the data from the out register, right? Accelerometer have this out register, it will give the data from out register. I want two registers for the giving for taking data, because these registers are 8-bit registers only. My data will be 16-bit. Okay, so but it has only 8 registers. That my registers are 8-bit. So I want 2 registers, and I will just do some like left shifting or some right shifting and all. I just adjust the data to make it into 16-bit, right? And this is final my 16-bit data, right? And there is some full scale value divisions and some gain values we need to division for this. For this, that we will use this, right? Since it is accelerometer, I'm just taking this. It depends upon how we are writing first initially. Let's say for example, so let's say for example, I'm asking my magnetometer to give full scale value something like some here, 12 Gauss. That means it will give in terms of 12 Gauss full scale value. So that we have to take at some gain value, that we have to take it as some gain value to the magnetometer here, 12 Gauss, right? So this all belongs to the 3 sensors. Let's say for example, 3 sensors with 3 axes. This is the accelerometer values with x-axis direction, accelerometer values with y-axis direction, accelerometer values with z-axis direction. Now gyroscope values with x-axis direction, gyroscope values with y-axis, gyroscope with the Z axis. Similarly, magnetometer also. Magnetometer X, magnetometer Y, magnetometer Z. Okay. So we are forming up to this. Up to this we finished. That means we are writing some data to the sensor, and also we are asking to give some data from the sensor. Now we are getting some data and you need to formulate the data, right? So we are forming the data here. Gyro, I'm just taking it a vector. This all data, gyroscope data is taking it a vector, and magnetometer data is taking it a vector. And so accelerometer is taking it a vector. Let's say, for example, now, so forget about gyroscope. First, we are getting roll pitch from the accelerometer and magnetometer, right? This is something called, I shown you previously, like we have to shift all the sensors in the individual sensor frames to the one sensor frame. That means that should be like I'm assuming like a PCB frame. So the frame should be with respect to the PCB or the board or drone. Okay. So these equations we already discussed. These are the equations I'm just keeping here. So these are the equations I'm just keeping here. Okay. These are the equations I'm just keeping here. Now we'll just print the data. We'll just see. We'll just run this and see the data. So you can see, right, how we are getting the data. Now this is roll, this is pitch, this is yaw. Right. You can see the roll, pitch, and yaw. Let's say I'm just moving this in terms of pitch. Middle one, you can observe middle one. It's moving, right? Middle one is changing data. Right? Similarly, I can move this in roll direction. First one, you can observe first vector. So this is negative, minus 98, minus 38 and all. And then this positive direction. Right? Then now I'm changing the yaw direction, like the heading direction. So you can observe this third column heading direction. So stop it now for now. And if you have any questions, please ask, and we'll move to the next, like after this. We'll discuss I'll show you the gyroscope values also, how to formulate. Any questions from the students?
Audience, you can ask the queries by unmuting yourself.
Till now, any questions from the students? Any doubts in the slides or any questions? Or if you are already working on some drones or already working on some estimation, if you encountered any problem, you can discuss. So I'm assuming no questions.
Yes, sir. There is no question. We can proceed, sir.
Okay. So same code only, same code. I'm just trying to formulate the gyroscope values also. Same code. Since we discussed already, let's say for example, in the slide, here we already discussed that we need some initial measurements from some other sensor, right? We can't able to, this gyroscope itself can't able to format this initial measurements for the next estimate. So I'm just dividing this loop into two parts, right? This while true loop will will enable the infinite loop for me, right? Let's say I'm just keeping this data. Let's say here onwards, I'm just calling this function read data once, only once. And I'm formulating these equations. I'm just taking it as initial value, pi naught, theta naught, and psi naught, right? Now I will go ahead and I will use the infinite loop. Similar to the previous code, I will use the infinite loop. And now here I'm just formulating from the gyroscope value. Like you can see transformation matrix here, right? This is the previous values, taking initial values. This is the transformation matrix. And I'm just doing integration of this. Let's say, for example, you can see here, this is the transformation matrix, right? I'm just doing integration of this. So by doing integration of this, and if I print these values, I'm just printing these values. And I'm just printing also these values, pi 2, theta 2, psi 2. Both values I'm just printing. You can observe these values, both. Okay. See, if you observe, if you can able to observe this in between the brackets, this is the gyroscope value, slowly moving. It's moving. It's going somewhere else. Its value. That means it's the integration is giving cumulative drift. It's going somewhere, right? You can stop and see. So it went up to minus 56. That means even though if my sensor is still standstill at position, but it giving some value, different values. So by using this, we use complementary filter by taking both values, complementary filter by using low pass filter and high pass filter. We'll combine both values and do. That's something you can do by yourself. So I'm not going to show this. Instead of this, I can show you something more interesting, like some animation we can try. Since this Raspberry Pi cannot able to afford the animations and all much, so I will try with the directly some other. I will try to take the data directly from some sensor to my computer by using this wireless transmission. Let's say, for example, you can remove this now. I'm stopping this. So this is the another test bed. Here, this is our own PCB developed by IPTIF here, the students, some students. So it has some microcontroller. I'm just doing same thing, what I done similar to this Raspberry Pi. I'm just giving data from this IMU. You can see IMU here. This is IMU. I'm just taking data from this IMU to the board, and then I'm sending to this wireless transmitter and receiver. Right, you can able to see this wireless transmitter, and this is something receiver that I will connect to my laptop. Okay. So this is called a PyCharm. This is an IDE, like Python IDE, where we can edit the code in the Python code. Maybe people can use some other IDEs like Thony IDE. Here we are using in Raspberry Pi this default inbuilt IDE is there for Python, Thony IDE. But here PyCharm I'm using in my laptop. So I think everyone can able to see my screen, right? So same code only, there is no change in the code. What I'm doing is I'm just adding some animation kind of thing. There is something package name called VPython, right? Visual Python I'm using. This is a package, extra package. I'm just using this. And I'm just first formulating one rigid body. I mean, I'm just creating some rigid body. Okay, with this global X arrows, I'm just keeping arrows also for the rigid body. And this base has some boxes that you can see. I will, once if you run this, you can able to see all these things, right? I'm just giving some bodies, rigid bodies. I'm just formulating all the rigid bodies. Okay. Now what I will do, I will just run the code and I will update the body orientation. This is my body. I'm just creating some body. So I will run the code and update. Let's say, for example, if you want to do some animations in MATLAB, what you will do? First, you will formulate the body, any body, by using this, by using line or by using any other thing. You will just formulate one body, then update. You will update your body every time, right? So the same code I'm using, and I'm just updating. Let's say, for example, here, first initially we'll see only with accelerometer and gyroscope. Okay, this is my body updation. Right? Here it will update the body. This is something called, we can use cross products and all. There's some Gram-Smith orthogonalization techniques they will use for some vectors. Okay, this is an updation of the body. Okay, let's say, for example, I'm getting the accelerometer values, things happen here, pi 2, theta 2, and psi 2. No need to bother about this gyroscope values. Okay. So I'm giving this pi 2 to psi 2 to here, these vectors, right? You can see psi 2, pi 2, something like that, right? You can see. So I'm just giving these values. I'm not bothering about gyroscope now. Okay. Now we'll just connect this battery here. So you can able to see this red color light is blinking. That means it's the data is transmitting the data. Okay. I'm just doing reset this. Now let's run this. Okay. So I'm just running this now. So you can able to see this body, right? This is the body. I'm just formulating some body. Okay. So you can see I'm just tilting my body from the screen only. So I'm just assuming I kept some plate is there and some two boards are there. My PCB and my Raspberry Pi and my sensor is there. And I also given some inertial frame for this. That means the frames are already every time attached to the body. And whenever I'm just updating, let's say, for example, now I will tilt this body. Let's say, for example, you can see the screen. I'm just tilting, right? You can able to see this. The small vectors you can see from blue, red, and the small vectors are with respect attached to the body. They will always rotate. But these big vectors are there, no? So those are not body frame, and those are belongs to the inertial frame. You can see. Let's say, for example, roll I'm doing, right? Pitch I'm doing. Yeah, I'm doing. You can able to see all the three directions, right?
Yeah.
But if I kept in the ground, let's say, for example, if I kept in the ground, so you can able to see only the vibrations, right? It's giving vibrations. That means the accelerometer is picking the noise, even small noise also. It's picking noise and it's giving vibrations. That means the drone is vibrating, right? You can't able to keep this type of vibration kind of sensor there. That means it will vibrate and will go and hit somewhere, right? Okay. Now we'll see gyroscope, only gyroscope behavior. Let's say, for example, we'll just remove this. So now what I'm doing, so my gyroscope attitude from the gyroscope is this. That means I'm just formatting pi 3, theta 3, and psi 3. I'm just giving some names for this. Pi 3, theta 3, and psi 3. Okay. So now let's change this. That's it. So I'm just updating my body with respect to the gyroscope values. Okay. Now let's run this. Let's run and see. Okay. I think some issue happened. Just a minute, it will come. It will come. Meanwhile, we already done with the whatever today's session. My intention is to show the Raspberry Pi content and actual formulation, how we'll do attitude formulation and role pitch. Yeah. Meanwhile, if you have any doubts or if you have any queries, please ask. Okay.
Previously we discussed like we are adding filters, right?
Hmm.
So will that filters help in avoiding the noises that we get through the linear acceleration? Accelerometers?
Yes, that will filters will help. Like a complementary filter, even if you actually what we have to do is for every sensor, first initially we have to apply low pass filter. Need not take very small bandwidth. You can take little high amount of bandwidth because every filter has some noise, some high frequency content will have. Every sensor have some high frequency content. So to avoid this, for every sensor you can apply some low pass filter, and then you give to the complementary filter. And accelerometer values you can give to the low pass filter again, and gyroscope values you can give to the high pass filter. And this is one way of representation of attitude. Let's say, for example, Euler angles. And there is another representation of attitude, like rotation matrix representation and quaternion method. Mostly people use quaternion method for some ready-made controllers. And let's say, for example, PX4 is there, Pixar controller, where they will use ready-made code for that, and they will use quaternion method. Every method of representation has its own advantages and its own drawbacks also. And this Euler angles more drawback is this singularity issue only, Euler angle parameterization. And other methods also has some their own drawbacks. We are not discussing about this. It's out of the scope of this discussion today. We'll try again. So if you see, there is no vibrations, but even though I'm not touching it at all, slowly it's moving, right? The body is slowly moving.
The initial object vertices, right?
Hmm?
That initial thing, right?
Hmm.
We have set already, right?
Yes. So even though I'm not touching, this is because of gyroscope. A gyroscope is drifting little slowly. If the same sensor you keep for the drone, you just assume how it will go, right? It will drift like this. Even though I'm not touching, it will slowly drift, it will go and it will become unbounded. Right. That is why people won't use gyroscope alone, or people won't use accelerometer, magnetometer alone. They will combine together and they will produce this attitude estimate. Right. You can see this. Right. Fine. So we are done with the today's session. You can try with this complementary filtering. I just shown accelerometer plus magnetometer values, and also show this gyroscope how it is behaving with the animation. You just apply just a discrete integration or discrete filter only. Right? We just need a discrete filter. You can apply this filter. You can able to get the good values. You just try. Everyone will try. Okay. If you try by yourself only, you can able to understand this, how to formulate this, how complexity will be there. And so if you have any doubts or questions, please unmute and ask, or you can chat. So there are some questions that I would like to ask you. This we already done because we tested practically with our drone and all. So I just told you that, let's say for example, my sensor, all sensors have different frames. Okay. Coordinate frames. And how can you convert all these coordinate frames into one PCB frame? This is my PCB, right? Different sensors have different coordinate frames, but I want to convert all these frames into my PCB frame. Maybe some coordinate frames are right-handed frames, some coordinate frames are left-handed frames. This is LHS, left-handed frame. This is right-handed frame. Okay. So to convert these things, just doing, let's say for example, just minus X will give the coordinate frame in terms of left-handed, right? But I derived my equations for the attitude by assuming right-handed coordinate system, right? Let's say, for example, this right-handed coordinate system, just some like middle finger will be Z axis and pointing finger will be Y axis and thumb will be X axis. This is right-handed coordinate system. So I derived these equations using right-handed coordinate system.
The other two.
Yes, but my sensors are giving left-handed coordinate system.
Yeah.
So how can we convert that also? You have to check. Okay. These are the common thing that people should take care while working on drones and all, because drones are highly unstable, right? If you do some mistake, it will go and hit somewhere. If it fall down, will miss out the drone. Okay. So, and one more thing is calibration. Calibration of sensor, all sensors. How can you do calibration? Let's say, for example, accelerometer and gyroscope calibration is very easy. Just keep in some standstill position and try to find out what is the drift and all. Okay, it's very easy for accelerometer, magnetometer, gyroscope. But how can you able to do for magnetometer? So magnetometer, how can you able to do? Because it has some tricky. We have to use some ellipsoidal technique, a least square technique, something that also you have to check. Okay. So this we already discussed how to select the corner frequency of the filter. Okay. By doing some DFT, by assuming some values of how much frequencies we need. Okay. This we use for this method. That's it. We are done for today. People, if have any questions. Or if you want to repeat anything, because we already we have still 10 more minutes. If you need more explanation in some concept.
Sir, sorry to interrupt. In between, the audience are requested to fill the feedback forms. Link is submitted in the chat box. Thank you. Any questions from the audience?
I will also share this sheet with you. Like how can we connect this I2C communication? Simple connections we have already given. This general purpose pins are there for Raspberry Pi. So I just connected this 3.3 and I2C serial data pin and clock pin ground. These three plus this one. These pins are connected to this ground VDD STA SCL. Okay.
Uses 3.3, right?
Yeah, this IMU uses 3.3. Yes. Let's find up.
Yeah, thank you, Mr. Vijay Kumar. I request Vishnu Narayanan, our admin intern, to propose the vote of thanks. Vishnu,
you.
please.
Yes, so on behalf of IPTIF, I would like to extend my heartfelt gratitude to each and every one of you for your presence and participation in our webinar series, Electroskies. First, I would like to thank Mr. Vijay Kumar Reddy for a detailed and informative session on IMU. Then I would like to thank all my colleagues who worked hard for this wonderful session. I would also like to thank all the participants who joined today. Do come back for the coming session on 17th and do spread the word to all your friends. Thank you. Thank you all for once again joining.
Thank you, Vishnu. Thank you once again to all. Thank you, Mr. Vijay Kumar. So shall we wind it up?
Yes, thank you.
Yeah, Noble.
Yes, ma'am.
Yeah, thank you. You can stop recording.